Okay, limits with inverse trig functions. So we're not going to go into too much detail with these. Okay, I will allow you to just say to yourself, well, when x goes to infinity, what is happening to this fraction here? Okay, so I'm actually looking at our cos of 0 here, right? Since this fraction is certainly going to 0. Well, it's going to equal our cos of 0 is pi over 2. Pi over 2. Okay, again, reasoning being that this fraction is going to 0. So I'm asking, what is our cosine of 0? That is what my function here is approaching. Okay, how about arctan 3 minus x squared? Now for this one, you're going to have to memorize, you're definitely going to have to memorize the graph of arctan. Got pi over 2 up here, got minus pi over 2 up here as horizontal asymptotes. So x is going to minus infinity. Oops, no, x is going to plus infinity, rather. So therefore, this expression in the rectangle is going to minus infinity. So I'm asking what's happening when I go along arctan way to the left. What am I approaching? Well, I'm approaching this minus pi over 2 here. Okay, so the graph of arctan is especially important in this class. It seems to come up over and over and over again. Okay, exercise. I want you to try this. So here you'll have, arc sine of, well, the numerator goes to just 2, and the denominator goes to just 4, since this item here on top is going to 0, and this guy on the bottom is also going to 0. So arc sine 2 over 4, which is arc sine a half, which is pi over 6. So my final answer is pi over 6. So this is me thinking about that. Okay, derivatives. So we're basically just introducing you to these new functions, arc sine, arc cos, arc tan. And we're going to go through limits. We went through them just now, and then we're going to do derivatives. And finally, we'll do some integration involving inverse trig. Derivatives, arc cosine. What to do, what to do, what to do. How can I find a formula for this derivative? So d by dx, you could also use arc cos prime if you prefer. Anyways, what do I do? Well, a little tricky demonstration here. I start with cos arc cos x is equal to just x. Now, what do I do now? Well, what do I want? Well, I want to find this derivative. So I should take a derivative of both sides. I do so, and I get this guy. So you're going to have to remember your chain rule. If you go f of u is equal to cosine of u, and g of x is equal to arc cosine of x. Chain rule says that you're going to have f prime of g dot g prime of x. Now on the right hand side, the derivative of x is just 1. And on the left hand side, I use chain rule with arc cos as my inside function. Okay, why did I do a thing like that? Well, because now this thing I want has appeared in my equation. So I need only solve for it, and I will be done. Okay, start by isolating the thing I want. And then I'm going to just simplify this denominator. Okay, sine of arc cos of x is something we did earlier in this chapter. Okay, I found earlier that it was the root of 1 minus x squared. So there you have it. Here is my derivative of arc cosine of x. Okay, I'm going to ask you to do one of these right now. Remember the steps. The steps are use the cancellation formula for cosine and arc cosine. Take a derivative of both sides, and then solve for the thing that you want. All right, try to find arctan prime the same way. So pause, copy, try. And the answer is 1 over 1 plus x squared. Okay, two things on the screen now. Here's a little summary of the derivatives of arcsine, arccos, and arctan. And here's my next example in the bottom left. Okay, nothing too special here, just mixing chain rule because of this 3 with the derivative of arcsine, which I'll grab from here. So, don't even show me, I thought I did this one. So this one's just chain rule, but 3 comes down. You get arcsine of x now squared. And then you have the derivative of the inside function in this empty bracket here. And that's this thing right here. And we usually write that as arcsine of x, leaving the squared outside usually. Though I won't be offended if you put the squared here. Maybe be a little bit offended, but I'll suck it up. Okay, nothing too crazy there. Chain rule. How about arcsecant of this square root? This one's a bit uglier. Arcsecant of x prime is 1 over x root x squared plus 1. Now, where'd this come from? Well, you can either memorize this, it's in the book, or you can derive it as I did above. Now, using chain rule, I get something unpleasant here. Let's just be careful here. I'll do chain rule carefully with f is my outside function, arc secant u. So f prime of u is going to be 1 over u root u squared. No, actually, that's -1, isn't it? Sorry, I made a bobo. This should be, this right here should be a minus. There's my f of u, and then g of x is the square root thingamabob, and I'll need g prime of x, which is dx over root x squared plus 1. To find g prime, I did chain rule. Okay, putting this all together, I get this thingamabunky is f prime with g plugged in times g prime. Whew, that's going to be unpleasant. So I'm taking f prime, and everywhere I see a u, I'm going to plug in this instead. So there's my f prime. So let's use a different color here. Purple, why not? Purple dot. Purple dot corresponds to a purple dot right there. And g prime is x over root x squared plus 1. Now, where are we? If I multiply this one and this one, I get just x squared plus 1 without the root sign. Root x squared. And then x here. Now, in general, root x squared is actually, if you think about it, it's equal to root of absolute value of x. But I typically allow students at this level to just not worry too much about such details and just cancel to get 1 over x squared plus 1. Okay, so a bit of a fudge there, but anyways, again, these are details that I'd rather not get hung up on. So I just said, well, this is x. We'll say this is x, canceling with the x on top. Wait. Anyhow, integrals, integration. So now we're going to be reversing the derivative formulas I gave you above. So if I take the 12 out, I will recognize this from the table given above as being arcsin. So every derivative formula yields an integration formula, and I use that here. Oops, did I do this already? Seems I've already done this, so let's just, I've already done this down here, sorry. Every integration formula, every differentiation formula yields an integration formula, blah, blah, blah. So there we have it. Plug in my 1 over root 2 and 1 over 2. Now for arcsine of 1 over root 2, that may not be familiar, this 1 over root 2. But it is exactly the same thing as root 2 over 2. You can see that by multiplying both top and bottom by root 2. Okay, so this is something that you'll recognize from the unit circle. So I can find arcsine of that, pi over 4. And arcsine of a half is pi over 6. And I work this out and get pi. So pause and copy. And we'll move on to an exercise for you to try. Okay, you'll need here to remember what this is. Okay, this is on the table I gave you earlier. So pause, copy, try. Now, I want to talk about notation for a second here. You'll notice I've been using arcsine of x. Okay, the textbook also uses this notation. The same thing. Okay, I've been using arcsine because I don't like this notation so much because it makes everybody think about this expression, but it's definitely not the same thing. Now we're using the word inverse. We can use the word inverse in two different ways. We can talk about inverses in the sense of a functional inverse. Okay, so this is arcsine of x. And this is, maybe you'd write this as sine x to the negative 1. Okay, they're very different things. Yeah, but I want you to be aware of this because the textbook does use this notation along with, cos inverse of x, secant inverse of x. Okay, but if you want to follow me, you can just use arc cos of x, arc secant of x.